Okay, so now we're going to try to design the ray tracer. So we have our basic primitives. We're going to send rays into the scene. We're going to intersect stuff. And now we're going to talk about which rays we're going to have to send to build up our ray tracer. So I'm not going to have you do this because we can't get in small groups easily. The breakout room stuff doesn't work out great. So when I teach this class in a regular classroom, I'm like, turn to your neighbor, write down the code we already talked about. There's less than 10 lines of code. So actually, maybe this is a good exercise. Grab a little sheet of paper or your notepad on your computer or whatever. Just scribble out the simple pseudocode. So we've given the pseudocode. It was 4 lines for how to do a ray tracer. So, and here's what it was. So for every pixel, construct a ray, and for every object, intersect that ray, the ray with the object. And we've left out one step, which was written in some of the earlier code, but I didn't mention. We have to intersect this ray with every object in our scene. Some will hit, some won't hit. Here I got 2, 1, 2, the backside of the sphere also, 3, 4 hits on this ray. I have to sort those hits. So now break out your, which class do we teach sorting? I don't know, 101. Break out your sorting algorithm and figure out which one's closest. And that's the one we're going to put in the screen, right? So we don't use a Z buffer for this. Because we don't know how many objects we're going to hit. I guess you could use some kind of Z buffer algorithm, or you could sort all the objects. But anyway, you somehow get the closest thing, and then we're going to write that color. So the complexity of this thing, the number of objects times the number of pixels, right? Because for every pixel, I have to go hit all of the objects if I don't have any acceleration. So I've got sort of n times m complexity, and you're going to see that this is gonna blow up as we go. Okay, here's our object so far. We haven't said anything about lighting. Here we've hit our objects. We've gotten some ray traced spheres in our scene. So now we need to add lighting to our code. So where is this going to go? Okay, so you all know where this is going to go because we just did it in our last lab. So we've found the closest intersection. Now it's time to run essentially our fragment shader. So we're going to loop for every light. You probably had 1 light in the last assignment you did, unless you went and added additional lights to your scene, right? And we had to pass the data for each light into the fragment shader. So we're typically going to have a list of lights. Add another loop for every light. This basically says run the fragment shader, right? Get the material and get the ray and the whatever, and go calculate all your directions and do your specular and diffuse Phong shading at this point, or more complex, whatever you wanted for your shading there. So our complexity is now nm number of lights. This is still not so bad, and we can speed this up to various accelerations. So this process can be sped up, particularly in terms of testing all of the objects. Okay, here's where we're up to. So this should be starting to look like what do we actually have so far in this class, right? This is a diffuse only. We didn't add the specular, but we have 1 light source in this scene, it looks like. We have a couple of objects. And so we've got our ray tracer up to here. And the number of lines of code to get here is somehow not so great, right? We just have to do some vector calculations on sending rays and compare everything. However, if you run this thing on the CPU, it's like I said, we're talking a long time to render this picture right here. Because for every pixel, right, and if I've got 1,000,000 pixels on my screen, I got to go do 1,000,000 tests of my spheres and find out what I hit and calculate the colors. You put all that on the CPU and it's going to get slow. Okay, now we wish we could get shadows, right? So here we go. We're adding shadows. They both interact on other objects and they land on this ground plane. How are we going to get those in? So now we have to think about where to add shadows to your code. So if you've been keeping a little notepad of our code so far, and what is our ray tracer so far, the question is, where are we going to add shadows? What do we do to add shadows? So who remembers what I told you was the answer to all questions in ray tracing? At a high level, what are we going to do to find out how to add shadows?
Send out a ray in space.
Draw a ray.
Yes, yes, correct. We're going to draw a ray. Now, we need to know which ray. So let me launch a poll. Let's see how people can think this through. So I've given some options here. I think this is more fun when I actually let people talk and give ideas, but I found that hard in Zoom, and you guys seem to like the polls, so we'll do it that way. To be fair, most of the questions I've asked you in this class in polls, I had previously given the answer in the, the 5 to 10 slides before I went and asked. In this case, I have not told you the answer yet, right? So I'm now, because this is a topic that you don't have to actually go implement, I'm now doing it in the other order. I'm asking you to think about it before we actually see what the answer is. Because I think it's fun to problem solve. And since you don't have to know this in order to do your labs, then I think it makes sense. We can do it this way. Okay, let me share these results. And we can see that we have lots of different answers. And so somebody tell us, what's your reasoning? I know you don't know. We'll see on the next slide what to do, but let's hear somebody's reasoning. Where are we going to send array? And how's it going to work out? Is anybody willing to tell us what they think?
Okay. Oh.
Go ahead, Jacob.
Okay. So I said C, that you send array to the light. But it was between C and D for me. But to me, it makes sense to send array from the light through the scene, and then you see like where it intersects with things, and if basically you color the last point it intersects with based on whether or not it intersected with any points before that.
Yeah, that's getting close to the right idea. So let me get a picture to see if I can help people with this, right? So here's our eye. I should have drawn a little plane in here for my screen. I've sent my thing through, and the first place I hit is on this ground plane, right? And I want to know, is this point in shadow or not in shadow, right? So this was my primary ray. Actually, let me annotate and try to make this thing work. So here's my screen, right? This is my ground plane. I've now hit at this point here. And we know how to run a fragment shader at this point. And what we've done so far is when we calculate our diffuse and specular, right? We have some eye direction, we have some lighting direction that we're calculating, right? And we have some normal direction at this thing. And then based on these vectors, based on these vectors alone, we went and calculated specular and diffuse and this sort of thing. We didn't have any notion of shadow because although we use this lighting direction, we don't know is there anything blocking or not, right? What's a shadow? It's when the light gets blocked. So now that we have this functionality of sending a ray, okay, our original ray had a point here in this direction. We're now going to create a new ray with the origin at our intersection point in the direction of our light, right? So the same L vector we had. And we're going to run exactly the same function call, right? So it's a recursive function call. We're going to use exactly the same function call that we had, and we're going to say, hey, what do we hit in the scene? And what was the closest point? And we know how far it was to the light, right? What's this distance here? And so if we hit any object which is closer, then that means it's blocking the light, and I must be in shadow. So this recursive call is going to tell us we're in shadow or we're not in shadow. We're not in shadow. Yeah, Kyle said this much more succinctly than I did in the chat, which I wasn't looking at. So this is, yes, so this is the way that we can deal with shadows. When we sent the ray from the light, no, we're not going to send a ray from the light, right? Okay, so we could send a ray from the light, but how would I know which direction to send it? The light is going in all directions, right? I don't know where to send it. So thinking about the photons coming out of the light is backwards. We're thinking instead in terms about this is the pixel, right? So right here's the pixel we're trying to color. We've sent a ray out into space, and maybe there was some more stuff in this scene, right? The ray didn't hit any of it. It hit this plane here. and this is the object we're trying to color. So we now send the ray from this point towards the light, the opposite of what was being asked in the chat. And so if we hit something else back here, right? If we hit an object back here, well, that's behind the light, so we don't have to worry about it, right? The light had better be the closest thing to the point in that direction. Otherwise, we were in shadow. Questions surrounding the shadow? Okay, I think we got it. So this idea of spawning secondary rays is going to be something that we're going to keep doing as we build up our ray tracer. What color would this be? So that's a great question. So somebody give us an answer. What color is it? Should be quite similar to what you've been doing in your existing lab.
Well, my guess is it'd be like the ambient light, but I don't know if that's correct.
No, we're going to run exactly the same lighting that you guys have been calculating. So this object has a color, right? Whatever this, right? I ran into this plane. So this is a triangle or a sphere or whatever it is in my world, right? This object has a color. Okay, the color of the object is that KD coefficient, or you passed it in as an attribute previously, right? So I have that stored somehow in this object, what the color is. Now, when I go do lighting, my lighting is going to be, my diffuse component of the lighting is going to be exactly n.L times the color. My specular component is going to be the I vector times the reflection vector, you know, dot product, some specular exponent something times the specular color, right? So I can do exactly the calculations that you did in a fragment shader. So it would typically not be running on the GPU. Most commonly, this would be implemented on the CPU. I guess if I was on a modern graphics card that supported this, I might be on the GPU in the same way, but I'm going to run exactly that same fragment shader. Oh, you're saying, what if I'm in shadow versus not in shadow? Okay. Now I get the question. Okay. If I'm not in shadow, it's exactly what you calculated before. If I am in shadow, I'm going to throw away the diffuse and the specular, and I'm going to be just the ambient. Okay, yes, now I understand your question, and you had the right answer, right? The ambient will always be there, but we throw away the diffuse and the specular. If I have multiple light sources, I might do this multiple times. So if I had another light over here, I might send a ray to this light and then a ray to the next light. Yeah, it's good you guys asked this question. I wasn't even getting it because, of course, I already know how it works, so I think it's obvious. Okay. So, by the way, some people implement this in the kinds of graphics that you've been rendering, right? So inside your fragment shader, we had one person in class who implemented shadows, and I can't remember if they used a shadow map or they did it this way. But inside your shaders that you wrote, I could cast this ray, right? I could say, like, I know where the light is, I know where that vector is, and I'm going to go find out if I ran into anything. But I would have to have access to the other triangles. So in your rendering so far, you know, when I'm figuring out the color at this point, I don't really know where this sphere is yet. So I can't easily intersect this ray. So I need global access to all the components. So this is one reason why we don't get the shadows as easily in the rendering you've been doing, because we treat each triangle completely separately. We don't have access to the global structure. Okay, multiple lights. I think I've already mentioned this on the previous slide. If we want to get to multiple lights, so that we can have multiple different shadows in our scene, we're just going to add a loop over each of the lights and calculate them separately, right? So here's a scene. We've got different shadows. We can see there's multiple shadows in here. So why is this section is darker? Okay, this is the color of the object from the texture, basically times the ambient, right? Over here, we have the color of the object, and one of the lights passed. So we got the diffuse term from the light that passed. But the other light, we didn't add the diffuse term. So this is basically, you know, whatever lighting times only one light. And then the same thing on this side. And out here, we have the lighting times two lights, right? So it gets even brighter. So you could implement, now this is not the shadows, but this notion of dealing with multiple lights can easily be dealt with in your existing renderer. But this shadow kind of effect, we don't have a way to get the secondary ray through the spheres. Okay, now we're on to our next add-on for ray tracing. So our next add-on is going to be reflection. So now, where are we going to add the reflection? So let me relaunch the polling. How do you think what are we going to do? So we know that the top level answer is we're going to send a ray, right? So all of these things say send a ray, send a ray, send a ray. Now the question is which ray, if we want to get reflection to work. Okay, you guys should be seeing the share results now. So we want to calculate reflection. So I think the dominant answer here is that we're going to send a ray in the reflection direction. So I have two possibilities now. One possibility is that people know why they want to send it in the reflection direction. And the second is that you guys have excellent test taking skills. And the word reflection appears in the question and it appears in this answer. So, hey, that's probably the right answer. So somebody tell us why are we going to send a ray in the reflection direction? And what are we going to do with it after we send it in that direction? Who can explain what we're going to do with this ray? I haven't told you yet. You're making a hypothesis. It's totally okay to be wrong.
Well, wouldn't we just take the color of whatever like we hit from the reflection direction and then add that in to what we have on our surface?
Yeah, that's a great answer, right? So we're going to send a ray in the reflection direction. We're going to get some color from that, and we're going to add that in. Okay, so first of all, what's the reflection direction? Okay, you've had the calculator use this, right? And you may have made a function call, or you may have gone and calculated it, but we have a ray comes into the surface. We have a normal. The reflection direction is just the equal angle reflection direction coming out. We have a reflected ray. So we can calculate what this ray is. And in fact, you had to do it to get your specular lighting to work right. So this is for a mirror reflection. Okay, here's a picture over here with a sphere, and we see the reflection of the other spheres. Here's our ray. Here's our reflected ray out of our scene, right? This is the primary ray coming in. We hit this point, we reflect out. So we're going to cast this ray. Oh, the black line's the normal. The orange line in this picture is my reflected ray. It's going to go off and hit something. And then we have to figure out what color this object was, and we're going to have to do something with that color. Now, if we have a pure mirror object like this, that means that basically that object's not contributing any color. So this sphere itself is not contributing color. What's happening is the ray is reflecting off, and if it hits the red object, we just stick red here. And if the ray hits this dark gray shadow, we just put dark gray. And if it hits the light gray surface, we just put light gray. Although we seem to have a specular component on this sphere because this highlight is coming from the specular highlight. Or maybe it's reflecting some object up here we don't see. Okay, so I could also have an object which is reflective but also has its own color. Maybe think of Christmas tree glass balls that you see, where they sort of have their own reddish color, but they also reflect the scene around them, this kind of thing. So I could have a color that came from my primary object, and then say, oh, it's only 50% reflected and 50% is coming from my color, and then I would add in the reflection. So you can have this notion of how much percentage of reflection, where this is 100% reflective object. Now we come to a detail. This is what this picture was about, this epsilon. So here's the detail. I hit this ray, and I calculated a new ray to go out in a new direction. Now, we don't have infinite precision on our computer. So when I calculate this ray in floating point, it could happen that my starting point is just behind the surface instead of just in front of the surface. And so if I don't take any special action, I just say cast this ray, find out what you run into, and get me the color back, then about half the time, because of floating point errors, my starting point is going to be inside this sphere. And so if I'm inside this sphere and I cast a ray, what's likely to be the first object that I run into? Well, the first object I'm likely to run into is the inside of this sphere, right? Just barely delta away. It's going to be closer than everything else. And inside of the sphere has no lighting, right? Because the light can't reach here, because every time I cast a light ray, it runs also into this sphere because I got trapped inside. So all those pixels basically return black for the reflection. So that's what you're seeing here. If I don't add a little epsilon when I calculate this ray, I end up turning half of my pixels to be black. So a common hack with no real justification and no proper way to set it correctly is that when I calculate these new rays to send away, either I offset the initial point by a little bit, or when I'm checking for closest object, if you get too close, we just say too close. I don't believe it, it's probably an error. And you throw those away. Does that mean you can make mistakes if objects get too close together? Yeah, you can make mistakes if objects get too close together because you didn't set your epsilon. But we set it to a tiny number on the order of the floating point error. And then you can get a clean picture. So there's a bunch of little details in getting a ray tracer right like this. So if you took a class where you wrote a ray tracer, we're talking about the simple code to get everything. But what happens is, you know, you go write the simple code and you get this picture and you're like, oh, great, what is this bug? Okay, it turns out you have to do this. There's a lot of those little gotchas in writing a ray tracer, just the same as what you've been doing so far in our class. Conceptually, it's not so hard. We have a vertex shader, we have a fragment shader, but I'm sure you've all suffered a bunch of bugs where you got weird pictures this quarter because of little gotchas that you have to do in order to get right. Ray tracing has them also, but they're a different set, right? We probably didn't have too many of these epsilon bugs in doing a rasterizer because we're not doing that kind of calculation. Okay, now, how much reflection should we pass? Well, it turns out that real objects are more complicated than just having a reflection and saying it's 50% light. So we can go get some tables of what happens for real objects. So this is the incoming angle from the normal. This is the amount of reflectance. So you go get these from like physics textbooks. People measure this stuff. And so here's a metal. And it says, and it's got it broken into polarization and unpolarized, but let's don't worry about the polarization of the light for this. Right, as our angle, incoming angle changes, the amount of reflected light changes a lot. And this is an extremely strong effect for glass, right? If I enter the glass at 0 degree angle from the normal, right? So I come in directly in the direction of the glass, there's not a lot of reflection. You basically see through the glass. And this is, I mean, that's why windows work, right? So we're all familiar with this end. If you get at a grazing angle to glass, then you get more and more of it is a reflection off of the glass. So the amount of reflection may be dependent on the incoming angle. So now how do we deal with that? Well, that's okay. We have, I mean, we're just have a function that does a calculation. We know what the incoming angle is. We know what the normals are. So before, and we're going to send this reflected ray, and when we multiply in or add in the light that came from the reflected ray, we're just going to take into account this more complicated function if we want to add those things. So it's not so hard to add these additional effects if we feel like adding. Okay, here's an example of refraction now instead of reflection. So there is both going on here. So we have, I mentioned for glass, right? Some of the light goes through the window and we see what's outside, and some of the light reflects off of the window, and so we see a reflection. So now here's a glass. So this white spot may be coming from rays that reflected off to the right, but it may also be coming from light that somehow went through the glass. So we need to get refraction now. And where are we going to add that ray? So before we go do our polling on where we're going to put our refraction ray, I see in the chat somebody commenting that we have to render the entire world in the reflection direction. Yes and no. So let me back up. I sent one ray in. This ray, if we have a perfect mirror reflector, generates one ray that's going out in another direction. Rendering the whole world from the eye involves rays through all of these pixels. So it's not true that every time I hit an object, I have to go render the whole world, right? Every time I hit an object, I just have to cast the one ray in the reflection direction. We'll get to rendering the whole world, but we're not up to that yet. But over the whole scene, if we had every object as reflective, then every one of these primary rays would make a secondary ray. So we would, in fact, have to render the entire world. But there's no single reflection direction, right? There might be a point that hits here and it reflects here, but the thing that hit the cube is reflecting off someplace else. It's not as if we rendered the whole world from this point. Because we don't need to so far up to our algorithm for a perfect mirror reflector, although we are going to come to that. Okay, refraction. Now we want to add refraction. So now, where are we going to add that thing? Okay, we have two dominant answers this time. Would somebody like to defend their answer and tell us some more details about where they're sending their ray?
Hi. So I said B. Because of a principle of like you just for refraction you just send a ray through the surface to the other side, and then at the point where it actually intersects the surface, you just offset the angle a bit to make a new ray.
Yeah, I mean, this is the right idea. It's going to go through to the other side. Does anybody have thoughts about exactly which way we're going to calculate? So for the reflection direction, for the mirror reflection, we knew how to calculate what that reflection direction was, right? So I can generate the new ray. I know the point, I know the direction. Now, what about the refraction? Does anybody know how we're going to calculate that?
This is just a guess, but like, do different surfaces have different like angles of refraction or something?
Yeah, good. It's called the index of refraction. So I have a light ray coming in. It's in air, which has a refraction index, right? And I have glass, which has a different refraction index because it has a different density. So the light gets bent when it crosses these surfaces. And then when it comes back out of the glass, right? So we're not going to just jump from this side of the window to this side of the window. We now have our ray traveling inside the window, right? And then when it gets to another level, it's gonna switch. So we don't just offset the position, it's a bend that happens when we change refraction index. So if we want to deal with transparent objects, this is another property we have to store. Just like we have to store the color and the reflectivity of the object, we now have to store the density so that we can get these calculations right. And do I not have it? All right, I got rid of a slide. Well, anyway, this is called Snell's law. And so if you took physics anytime recently, you may remember it. I'm sure you studied something about this, right? The light gets bent, and there's a precise formula that tells you how much it gets bent based on what these index of refractions are. So it's pretty easy to calculate something that looks reasonable. And if you want it to be a glass object versus some other object, you just go look up what are these indices of refraction, and it'll do the right. So here's a picture of a refractive thing, and this is the typical kind of effect you see, right? Things get kind of bent and warbly behind. I'm sure you've all seen this because I'm sure you all look at the real world, right? And you have objects which are made out of glass, and they make this kind of effect. So you know what it is that you're trying to see. So you can get this kind of effect to work quite nicely and easily in a ray tracer by just sending an additional ray in those directions. So now there's another point that comes up here. So for our transparency, so we had our ray, we had our normal. We previously had a reflection here. So now we're going to cast a ray through this object. It's going to get bent again, and it's going to come out here. And it's eventually going to hit something else, right? Let's say it hits this blue cube. We have to propagate information back, right? So far, we've only had one bounce. Now we're starting to get up to multiple bounces. So the color at this point is the color of this sphere plus, which might be nothing because it's supposed to be transparent, or might be just a little bit of red or white or whatever, because it's supposed to have some of its own color. Now we have a ray that went in, and then we're going to do the same calculation here and then recursively call, and the ray is going to go down. So we may be several bounces in before we got to an object that really has a color. This blue is going to propagate up to change the color of this point, and then that's going to propagate back to change the color of this point, right? So these are recursive calls. Like, what's the color here? Whatever came from this incoming ray downstream, we don't know how many bounces it might take. And then we're going to add that in 30% or whatever is the fraction for the calculation that we're doing, plus the local color, plus the reflection color. So I can end up with essentially a tree. Okay, so here's my primary ray. So this picture looks a little different because I swiped it from another place, but it shows all the rays and I think makes this more clear. Here's my primary ray. I hit this point. I need to send a shadow ray to find out for my local shading. I have a reflection ray. I have a transmission ray. But this transmission ray, when it hits the next surface, in turn has a reflection ray and a transmission ray. And the reflection ray has a reflection and a transmission. And each of these is spawning two. So I've now, and every time there's a point which might be in light, I have to send some shadow rays. So now to color this one pixel, well, I got a whole bunch of rays I had to send. And somehow, at this point, we're going to add up this local computed color value plus some fraction of the incoming reflection plus some fraction of the incoming transmission, and add that up and get this point. But to get this, we had to, again, do that add up of things downstream, right? So I end up with this whole tree structure to get a color back here. So you're starting to see why is it that ray tracing can get slow? Because it's so easy in your code to say, like, I already wrote the code to intersect a ray with the scene. Let me just call that function again, no problem. Like, oh, I wanted refractions too. I wanted reflections. Oh, but now I got this whole tree instead of only a single ray. Oh, add my shadows for 14 different lights. Okay, no problem. But it starts adding a bunch of rays, and things start to get slow because we can add so many new kinds of effects so easily in terms of reusing the same code that we had previously. So here's a picture from, I didn't take a note. Bad citation of me. Didn't make a note of where I stole this from. But anyway, here's a more modern ray tracer and an example of the same kind of thing I was showing you, right? We send one ray into the scene, and like we got all these bounces around trying to calculate what's going on to get the color at one point. So this happens. Yeah, how do you handle two mirrors facing each other? Some max bounces? That is an excellent question. So the first order answer, if I asked you to write a ray tracer for this class, the first thing people would do is nothing, and then their code will run an infinite loop, because exactly, if I have two mirrors facing each other, I just get rays that bounce back and forth, and like they never exit my scene. So yeah, then you stick in a max bounces. That's one way to deal with it. Another thing you can do is to, when we're doing this calculation of adding up, let me go back to this picture. At this point, this reflected ray, let's call everything 50%, because it'll make our math easy. This reflected ray is going to add 50%. So I'm going to have 50% of my local color, and I'm going to have 50% reflected. Now, this one is going to spawn some new rays, but I'm really not interested in the color of this ray. I'm only interested because it contributes to my primary ray. So I know that I'm down at 50%. And now I have another reflection. Or let me do the transmission. Now this transmission is down at 25% contribution, right? Because it's only going to be 50% contribution to this point, which in turn is 50% to here. So this ray is only 25% to my final color. This one is only 12% of my final color. So once I get down to, let's say, less than 1% change in color, then it really doesn't matter what color the ray comes out. It's not impacting anything in my final calc. Like, I can't see the difference. So then I can cut off. So I can also keep track. And somebody else that mentioned, how about the max distance the ray traveled? I don't see people using that. And the reason is because things could be spaced quite far apart, and you might still see the color. So if you had some kind of fog in your scene that was attenuating the ray, it might make sense to use a ray distance traveled. But it's more common to use either just a max number of bounces or the amount of energy left in the ray that can contribute. And in fact, you would frequently use both, because the two mirrors facing each other, if you set those mirrors to be 100% reflective, then you're just going to end up, it's still never going to converge. But real mirrors are not 100%, they're like 90%. So, and they have some local contribution. So having really 100% reflective objects is a rare thing in a scene. So this was a great question, right? This is another one of those gotchas. Like, this is this corner case, you got to handle it. Indeed, when I was when I was an undergraduate, I was really into my graphics project, and I went and told, we didn't have something equivalent to a senior thesis, which you guys have an option to do. But anyway, I went and told the professor, like, I want to do a project. I want to figure out what it looks like on the inside of a sphere, because I had a sphere and I had a ray tracer. I'm like, I'm going to put my camera inside the sphere. I'm going to put a light in there, and now I'm just going to trace rays and find out what do you see. I never got that to work because you got to put a model of yourself in there, or I don't know what you have to do, but like, I never got a picture which made any sense. So I didn't succeed in trying to do that, but it was my grand idea of like, I'm going to try this out and see what you see if you're stuck inside of a mirror sphere. Okay, questions so far on tracing rays. So we've gotten up to a basic algorithm. We can handle shadows, we can handle reflections, we can handle refractions. So in some sense, in half of the lecture so far, we've gotten further than we got in a whole quarter of trying to do the triangles. That's maybe because we're skipping a bunch of details about what's in there, right? If you had to go write it, it would take longer, right? Like, we're leveraging the fact we already spent our whole lecture on lighting. So I was able to just gloss over lighting and say, do this, do the same thing. I'd say that the two methods are about the same. Anyway, questions up to where we are so far?